Hey guys, welcome to video 4.2.1. In this lesson for 4.2, we are going to be just working out 7 different kinds of problems. 7 different kinds of problems and explaining, all the different types of these acid-base solutions. So there are many types of these acid-base solutions that you're going to come across, so it can be confusing for how to approach them. For every kind, you need to 1. Identify the type of substance in the problem. 2. Represent what's happening in a chemical equation, so you're always going to have to write an equation. And 3. Have a strategy, so I'm going to teach you how to do that today. The first one, we're going to look at a 0.1 molar hydrochloric acid solution. Now, hydrochloric acid is a strong acid, so this type is strong acid. Find the concentration of all species, the pH, pOH, and the percent ionization. Okay, so our strategy here, this dissociates 100%. So we have 100% dissociation. So that means that the 0.1 molar hydrochloric acid solution is going to be equal to the hydrogen ion concentration. So 0.1 molar hydrogen ion concentration is going to be here, and from that you can find your pH, pOH, and everything. But I'm going to show you that through an ice table. Now, if you have a strong acid or a strong base, you don't actually have to use an ice table, but I'm going to show you that way anyway. So we have our hydrochloric acid dissociates a one-way arrow because it's strong into H plus and Cl minus, hydrogen and chloride ions. ICE. HCl is aqueous, so this is a solution, so we can't just cross it out. So we're going to start with a 0.1 molar solution, 0.100 molar, and then we haven't formed any of our ions yet. Since this dissociates 100%, it's not going to be minus X, but minus all of it, because all of it dissociates. So we already know what that is. We already know what that X is, minus 0.100 plus 0.100 plus 0.100. So in the end, we know we have no HCl left over, and we have 0.100 molar hydrogen and 0.100 chloride as well. So that makes sense. Since this is a strong acid, we don't have any of the whole solution left, and we just have the ions dissociated. Okay, so our concentration of all the species, that means concentration of everything here. The concentration of hydrochloric acid at the end, that was 0. Concentration of hydrogen ions is 0.11, and again, you're looking at the ending amounts here. Concentration of chloride is the same as hydrogen, 0.100 from there. Concentration of hydroxide equals 1.0 times 10 to the negative 14 over 1.0 times 10 to the negative 1. And that's because here we have our concentration of, or this is our Kw. So if you remember, Kw equals H plus concentration times OH minus. And so this is the equation that we rearranged here. So we rearranged it to solve for OH. Just go ahead and divide both sides by hydrogen, which I did here. So your hydroxide ion concentration is equal to the Kw. So Kw, remember, we're always assuming we're at 25 degrees Celsius unless told otherwise, is always 1.0 times 10 to the negative 14. And our concentration of hydrogen ions is 1.0 times 10 to the negative 1, same thing as 0.1, just in scientific notation. So that's how we can find our concentration of hydroxide, 1.0 times 10 to the negative 13 molar. Okay, so finding our pH. pH is equal to negative log of the H plus concentration, which is negative log 1.0 times 10 to the negative 1, which equals 1.00. pH is 1. pOH, remember pH plus pOH equals 14. So 14 minus 1 from here equals 13, so our pOH is 13. And their percent dissociation. Percent dissociation is just a ratio really here. So it's the amount of ions that dissociated, right? So you can just pick one of these ions, pick the hydrogen. So the concentration of the ions in solution over the initial amount of whatever you started with. So here I had 0.100 ions, and then I started with 0.100 as my concentration for my entire HCl. So you can see that this is 1, and then of course times 100% to get a percentage, and you should get 100% dissociated. And that makes sense, again, because this is a strong acid and they dissociate 100%. So that would be it for your strong acid. Now let's go to the next problem. Consider a 0.100 molar calcium hydroxide solution. So again, we're going to do the same thing. We're going to find the concentration of all the species and the percent ionization. Calcium hydroxide, of course, is a strong base. Strong base. And our strategy is still 100% dissociation. Okay, at this point, I would like you to pause the video and see if you can tackle this problem. Keep in mind that this dissociates into calcium and hydroxides, and keep in mind you have 2 hydroxides here, but really that's the only change that you're going to end up having. So go ahead, pause this video, and see if you can tackle this problem. Alright, let's go ahead and start with writing the chemical equation. So we have calcium hydroxide, which is CaOH2, one-way arrow, dissociates into 1 calcium ion and 2 hydroxides. Initial change ending. Okay, so I started with my concentration of 0.100 molar here, and of course I haven't formed any calcium or any hydroxide yet. This dissociates 100%, so I know all this is going to be gone. I add 0.100 calciums there. Here, I have 2 times that amount. I'm going to carry this 2 down, so I have 2 hydroxides. So 2 times 0.100. My ending amounts are 0, 0.100, and 0.200. So writing my concentrations of all the species, calcium hydroxide, concentration is 0 molar. Concentration of calcium is 0.100 molar. And my concentration of hydroxide equals 0.200 molar. Okay, finding my pOH equals negative log of my OH concentration. So that's going to be negative log of 0.200. Plugging that in, you should get 0.70 for your pOH. And that's good. So this is a base. It's a strong base, so it should have a really low pOH. So it would have a really high pH. So the pH is going to end up being 13.3. So let's see that. pH, of course, is 14 minus your pOH, 0.70, and that equals 13.3. So very, very high pH, indicating a base. Very, very low pOH, again, indicating a base. Your hydrogen ion concentration you can derive using that same way that we did before, remembering that Kw equals H plus times OH minus. So I'm going to rearrange that. H plus is going to be equal to my Kw on top, and Kw, remember, is 1.0 times 10 to the negative 14 over my concentration of my my hydroxide ions. So that's going to be 0.200. Plug that in, and you should get 5.0 times 10 to the negative 14th for your H plus concentration. Alright, my percent dissociation is going to be equal to the ions over what you initially started with. So I initially started with 0.100 molar solution. And here, the ions that dissociated came off in increments of 0.100 molar. So we're going to use that number there. We're not going to use the multiplied out version. Because we just have 2 of these, we're not taking that into account. We're just going to use 0.100 molar times 100% equals 100% dissociated, which makes sense because this is a strong base, so all of it breaks up in solution. Right, that's it for problems 1 and 2 and video 4.2.1.